Hello once more. In our last video about the Phonon correlation function for as the correction to the electronic Green's function when we have just electronic levels vibrating with the mode h bar omega 0, and where electrons and this mode are coupled by a coupling constant lambda. So in this case, we derive the correction to the electronic correlation function with this Phonon correlation given by a t prime, that, as we see here, depends on the difference between t and minus t prime. This is what we got last time, and then we said that we can just let's erase a little bit the spot here to just create some space, and then we said that the total electronic Green's function was just the product between the purely electronic part with no vibrations times this correction ATT prime that I just have been calling throughout some videos as the Phonon correlation function. And this is just it's not a Green's function, it's just a correction to the Green's function, a multiplicative correction. Then if we calculate the Fourier transform of G, then we get that we have, of course, we can only calculate the Fourier transform if both of these kernels depend on the difference between t and minus t prime. We integrate with respect to t minus t prime, and then we get as follows: G sigma prime of omega. So we want to elaborate this a little bit, and it says that to do so, we reconsider that expression for the correlation function ATT prime, and we just look at this term. So then this is what we want to do. So we want to elaborate on this term. So this is not going to take us so long, hopefully, and then we elaborate in the following way. So we're going to do, so basically here what we have is that pretty much we have some constant terms. So then we have this term, which is just this 1 times this 1 is a constant term. We have nb times 1 is just 1 nb, and then we have here this 1 times nb, which is the Bose function. And then if we gather all together, we get this factor of 1 plus 2 nb. And then the rest that actually multiplies either e to the minus I omega 0 t minus t prime or e to the plus I omega 0 t minus t prime, we just put it here in the separate term. And then so we take out a minus sign here, because this is a minus sign and this is a minus sign, so this minus here becomes a plus, as you can see here. And we just recall the expression for this AT of t prime, and then we said the following. So we said that expression was given by this, and then now we can just say that this expression can be further factorized as according to this movement that we did here, can be factorized in these two terms. So the first term is this that just contains both functions and no times here. So this is the time independent factor, and there is this factor that, of course, again depends on the difference between t minus t prime. And then we write g in the following way. So we write g as this, so we take this one outside the integral. We have this integral here, and what we're going to do for calculating g of sigma prime, we just have to evaluate this integral, which is well, it's not trivial, but it's not too hard either. So then what we're going to do is the following. So we're going to make this substitution tau equal to t minus t prime. So this is what we have: e to the minus I omega 0 tau here, e to the plus I omega 0 tau here. This is tau variable here, tau here, tau here. So a bunch of taus. Now we have replaced t minus t prime for that. And what we're going to do is that we're just going to look at the following. So then see that we had pretty much express, or let's say divide here by nb of omega 0. Yeah, so that we can do, and then we get this, and then we're going to see what is this. See, so then we just replace by the factors, by the definition of the Bose function here. It's easy to elaborate a little bit. So then here we just add these two terms to give this. We just keep this here, and then we just see that these two terms cancel each other, and then this term cancels this term, and then we end up with e to the beta h bar omega 0, which leaves us with saying that the square root of that is nothing but this thing here, which if you cannot see it because of the lines, so it's e to the beta h bar omega 0 divided by 2. Okay, that's what we have. So then actually square root of that, and then so then we're going to transform that integral a little bit. So we have just wait, because we have this nb of omega 0 here. So where does it come from? So then let's see. Yeah, so we have divided everything by mb. Yeah, so then divide here by mb omega 0 as well. So then these two cancel each other. This is where we got this from. That's right. And then but why we have this one left here? That's what I don't quite recall. Oh, no. Yeah, of course we divide. If we divide here, we have then to multiply by nb omega 0 here. That's right. Or this is equivalent to just factorize nb omega 0 out of this term here. And so we have, it shows that here. That's right. So then we have it here from the factorization. And then since we saw that term, this full term gave this, so then we are left here with this term here. And what we're going to do is that we're going to split a little trick here. This any term, so for instance e to the a, it can be said that this is equal to e to the a halves times e to the a halves. So this little trick we have played. So by replacing this e to the beta h bar omega 0 by e to the beta h bar omega 0 half times e to the beta h bar omega 0 half. And on the other side, since here we don't have any e to the beta h bar omega 0, but we have a 1, and we know that e to the a divided by 2 times e to the minus a divided by 2 is equal to 1. So that's what we're going to do here. So we're going to multiply rather two exponentials, but with one argument will be positive, the other argument will be negative. See, so then that's what we have here. And then we just simply can factorize e to the beta h bar omega 0 here out. That's what we do here. And then we're left with this. See? And of course we can just factorize both exponentials in this way, as you can see here. See, quite nice. And then we're almost done with this. We have this term here. So we can just see that this term here, this is just recall Euler's identity. which says that e to the I theta is equal to cosine theta plus, if this is plus minus here, this is plus minus here, I sine theta. Okay, and then if we just add, if we have one expression with a plus and one with a minus, and we add both expressions, then we get the summation of two complex exponentials with one argument being positive and another one being negative, and then what we'll get is just 2 times the cosine of the argument, which is omega 0 tau plus I beta h bar omega 0 2. Okay, and that's exactly what we're left with here. Here's the 2, here's the cosine, and then here's just some expansion that we have studied before in the channel. So just in the channel, just look for the Jacobi-Anger expansion that says that e to the z cosine theta is the summation from minus infinity to plus infinity of some polynomial in of z. That's the complex Bessel polynomial times e to the I n theta. So then we say that noting that the above expression appears in the integral. Of course, it does appear in the integral. So what we're going to do is the following. So just see that we have e here. This is exponential. We have some term here that will be z. And then we have here the cosine of theta. What is this equal to? So this is just equal to all of these things here is just the summation and minus infinity to plus infinity of what? This generalized Bessel function of z, which means is the, let's write it down explicitly, is the generalized Bessel function of what? Of 2 lambda divided by h bar omega 0 all square e to the beta h bar omega 0 whatever 2 times mb of omega 0. See, and then of course we know that all of this is z, so then that's what we're doing here, just writing c instead of all that. So this is z e to the what? I n theta. But what's theta? So actually theta is this here. See, so then this is omega 0 tau. This is plus I beta h bar omega 0 divided by 2. So this is what this part is equal to. So just by this identity, see, this is what we define for z and for theta, and then we just move forward. So then we split this parts here. Now we know that this is the Bessel function we need to calculate or evaluate. We're not going to do that here because that's for specific values of lambda and omega 0. We have this term here. We're going to see something quite nice in just a minute. So then just carry out here the calculation. So this depends on tau. This doesn't depend on tau. Okay. So then, and we will just pull out everything that doesn't depend on tau outside the integral, or we will just pull the integral somewhere here inside, and this doesn't depend on tau, we will pull it outside. Then we'll end up with something like this. Okay? And then what we have is that we just have nothing but this harmonic summation in Bessel harmonics. And then we have this integral here, which how will that look like? So then this looks like something. So then actually this here is nothing but the Fourier transform of this function k sigma sigma prime of tau, but evaluated at omega plus n omega 0, which is what we have here. Okay? So then this is the value of the integral, and then we were going to go here and see what we have. So then we have that the total Green's function is just this factor that we already calculated before, times this integral that we were left with in the very beginning, and after the evaluation what we have is just this factor remains, times the summation of these Bessel complex Bessel functions evaluated at this number here, which depends on the electron phonon coupling lambda, depends on the frequency of the mode omega 0, this exponential here, and of course the Bose function of this will actually depend on temperature. So this thing here is dependent on temperature, okay? And basically what you have is that you will have more harmonics when you excite this with temperature. You'll have less harmonics when you decrease the temperature. So this thing here is a function of temperature, okay? And you just multiply this by e to the minus beta h bar omega 0 divided by 2 times this this here Green's function, and evaluated at omega plus n omega 0. So what that means, this is basically what this means, and I will explain first and then I will come back to just discuss what it says here. What that means is that we basically have a Green's function, total electronic Green's function omega, that goes as some summation. There is some constant here. So some summation from n minus infinity to plus infinity. Of course here of some harmonic, because this is in of z, and this is some harmonic. And then depending on the value of z and of the value of n, so we will have different harmonics, like when we have Fourier harmonics, that we have these harmonics. Each of these Bessel harmonics, what it will do is that it will weight the electronic Green's function evaluated at omega plus n omega 0. See? So then this will create displaced versions of the Green's function depending on the value of n. So then for n equal to 0, for instance, you can have a Green's function here. For n equal to minus 1, you will have a Green's function here, maybe with less amplitude because that will be weighted by this factor here, see? And then for this equal to plus 1, and it will be here weighted by some other factor. So then at the end what you will get will just be sort of bands, of infinite summation of bands, and where you can just truncate this sum at, I don't know, n equal to 10. I usually, in one of the papers I wrote using this method, I truncated at n equal to 20, and then you will have all of these bands here, and these are called phonon sidebands because it's the phonon mode. They're responsible for the generation of these multiple bands in the Green's function, and these will be seen with much more detail when you calculate the density of states, which is nothing but minus 1 over pi in equilibrium, the imaginary part of the trace of g sigma sigma prime retarded of omega, okay? And then you will see some bands that emerge from this summation here. So in general you will have like a Laurentian here, but then when you have phonons, then you will have these bands. These bands are called phonon sidebands, and they will have some interesting effect on the physics of our system that we will discuss in a different video, I promise. So for the meantime, let's think about what can we do here. So where's the physics of the above result? So pretty much the physics is that since now you have, before you had just this density of states with just a single mode here, now you have this, all of these let's say sidebands here, as I show you. So now you have multiple modes. What that means is that the phonon, the interaction between a phonon and a single electron level, is equivalent to a system of many energy levels, infinite energy levels, where the spacing of each energy level between, of course, between energy level and energy level is just h bar omega 0. Okay, that's the spacing between these two levels. So then, for instance, this is E0. Here, this is E0 plus h bar omega 0. This here will be E0 minus h bar omega 0, and such and such and such. That's the physics of our result. And of course, as I mentioned in the very beginning of the first video we did, that the energies, the interactions are renormalized. So what's that mean? So it means that, for instance, as we saw in the video for the Lanfear-Stokes transformation, just let me show you quickly what that means. That means that when you have phonons, so your E0 now turns into some E0 minus lambda squared divided by h bar omega 0, and your electron-electron interaction now turns into the same electron-electron interaction minus 2 lambda squared h bar omega 0, where you can see from here, of course, that phonons eventually will make this interaction attractive from being repulsive. Okay, so you can go from repulsive to attractive by the aid of phonons. That's another physical result of this theory. And then what sort of observables can we compute from it? So that's a question for a different video, as we can, for instance, see the effects of phonons in electric current, in spin current, and the density of states, as I show you just in brief just before, and stuff like that. We're interested in entropy and quantum coherence and related quantities. And then how can we proceed? Because what has been shown is that the electron-phonon interaction, actually, the electron-phonon interaction, what it does is that destroys quantum coherence. So then you can go on to the coherence situation with lambda. Lambda and the coherence are related. Okay? And the coherence and entropy are related. Remember that a system that for the von Neumann entropy minus the trace of rho logarithm of rho, this, for a coherent realization, this entropy will be less than for a decoherent realization. So when you actually have decoherence, so the entropy for decoherence is greater than the entropy for coherence. And this has to do with the electron-phonon interaction. So then we can ask this question over and over for just simple systems, some atoms and levels coupled to electronic reservoirs. So this is what we can do with this. Of course, this is not done. We will post more videos on this electron-phonon interaction. This is very interesting physics, not so much treated in the literature, so then we will do the effort to do it here in the channel. So thanks for watching for now, and please subscribe and like if you enjoyed the video. Bye bye.